There will come a time on the planet Earth when science and technology will be long forgotten, when humanity will rise from the ashes of nuclear holocaust, when wizards will rule the world.
If ever a wizard walked this earth, he went by the name of Leonard Euler, a master mathematician whose spells have remained at the heart of modern-day science and technology. And it is this formula, the formula for the complex exponential, that has cast a spell on me ever since I learned about it. It is a connection between complex numbers and trigonometry. And that connection, it turns out, allows us to do some very real things by accessing a seemingly hidden or imaginary dimension to the world we live in. Extending the real numbers into the plane of the complex numbers, the trigonometric components and the various identities associated with them give rise to a rich set of formulaic tools which have some rather cool applications. For example, raising a complex number to a power can be calculated using the multiple angular formulas in trigonometry. And a central tool in signal theory, as well as in quantum mechanics, is the well-known Fourier transform, whose kernel is a complex exponential. So you see, the work of the wizard Leonard Euler is something to marvel at. And today I'd like to show you an example of using Euler's spell on a fun integral. Consider this integral of e to the negative x sine of x dx. Pause the video now if you'd like to give it a try. In a Calculus 2 class, you'd use integration by parts to attack this integral. And this integral would require actually two integration by parts. So let's see how that would look before we reveal the magic of Leonard Euler. So in the first run through, we'll let u equal sine of x and dv equal to e to the negative x dx. And calculating du and v from those components, we then can write out what the integration by parts formula would give us, and then realize that second integral we have to also use the integration by parts formula for. But when we do that, we'll return to the original integral that we arrived at, and you'll see how this is going to work out. So that second integral will use u as cosine of x and dv as e to the negative x dx, and find du and v from those components. Plugging that all into our big integral formula here, and simplifying the results, we get I is equal to negative e to the negative x over 2 multiplied by sine x plus cosine x plus some integration constant. Not a terribly difficult integral to do by a Calculus 2 standard. But what we're going to do is this same integral using a different approach, a more complex approach. Wielding the complex exponential, e to the I theta equals cosine theta plus I sine theta. The real part is the cosine theta. The imaginary part's I sine theta, where I is the square root of negative 1. But the sine part of that is also a real component. Now to attack this problem by complexifying it, we'll observe that the integrand e to the negative x sine x is the imaginary part of e to the negative x times e to the ix. And since by the rules of exponents we can combine those, If we substituted that into our integral, we can then rearrange this in a way that says we just want the imaginary part of the integral of e to the negative 1 plus I x dx. And because finding the integral of an exponential is rather easy, we get the result e to the negative 1 plus ix over negative 1 plus I. Now, we don't want to leave that complex number in the denominator, so what we're going to do is we're going to change the form of that just slightly. So we'll recognize that 1 over negative 1 plus I can be changed into negative 1 minus I over 2 by multiplying the top and bottom of that fraction by the complex conjugate, therefore eliminating the complex number in the denominator. And then once we take this and we divide out the real and imaginary parts using their complex trigonometric components, we can pull out the imaginary part from that expression, which is going to be what our integral is equal to, and wouldn't you know it, negative e to the negative x over 2 multiplied by sine x plus cosine x plus some constant c. Truly a magical experience. This is one of my favorite formulas in math, and I hope it's one of yours. It truly is magic, and I hope you enjoyed this video. Please hit that like, subscribe, and notification bell for more videos, and stay tuned for the next one. Thanks for watching, and thank you, Leonard Euler, for your magic.